Hey, we're live. Just getting all set up. And we've got a really nice comment from Vasil. And man, that's so good. I'm glad that you wait. I'm glad you're here. I've already got 8 people here, it looks like. That's, man, even a little bit early. So thank you for joining. And hopefully we've got some cool stuff to show you. I'm kind of running behind. I had a lazy morning because it's actually a day off for us NVIDIAns, but I love doing this. I love doing this live stream too. So love being here. Love sharing this project with you all. And yeah, leave your comments, leave your feedback. But let's get started. Let's see here. I think first let's pop open Isaac Sim, and I just want to show you where we're at. Let's see, here's Isaac Sim. And we'll get people rolling in here. So let me just making sure my stuff's in the right windows. Here we go. Let's go ahead and share that screen. All righty. And we have got Isaac Sim. We're getting this going here. Yeah, so if you remember from last week, we demonstrated a pipeline where we have this assembly in CAD, and then we import that into Omniverse, and we do that with sublayers, and we organize it by subassembly, by subcomponent, so that we can exchange the CAD meshes later. And in particular, right now I have a very simplified design, and I just have an assembly that says this is the assembly that will contain like the lower left A-arm, for example. But in the end, that's going to be, it's going to be an assembly. It's going to be a couple of parts. It's going to be some rod end bearings, and it's going to, if you look at my remote control car, one of the lower control arms, a lower front control arm, is the actual piece of plastic, and then it's 3 spherical bearings. And in the rear, it's the same thing, but it's got a pin. And so eventually we'll want to add all of those, I think, to get a really good looking, we want it to look good by the end. Right now, we're just trying to get it going, but by the end, we want it to, I think, look really sharp. Let's see here. We're getting a slow start here. There we go. And of course, I'm not logged into the VPN. Just a minute. I've got to get it to my Nucleus servers. That's where all my data's at. And there you go. Just give me a second here to log into that. Oops. Authenticating me with my face. Just a minute. There we go. I'm back. Connected to VPN, and so it dropped me for just a minute, just a second there. Let's reconnect to, there we go. Now we're connected. And here we got the JetRacer folder. Let's open this up and see where we're at. So last week I showed you how to bring that stuff in. I showed you how to rig the suspension. I think I even showed you how to set limits on the shocks. And what I've done during the week since then is I went ahead and rigged up the other side of the suspension, the right-hand side. And I also did the steering here. and I tweaked, I looked up the units in Isaac Sim. I got my chassis really weighs like a kilogram, whereas the arms weigh like 10 grams. So I think getting some of those weights right helped. I also wrote this little extension that lets you connect to the car and drive it with a gamepad. So here in my hand, I've got a gamepad. Doesn't really matter as long as it's USB. So let's run. So I hit this connect button, and now I'm connected. I hit run, and you can see the car's on the ground now. And I am steering this with the gamepad. Cool, right? And I'm going to hit the throttle here, and we're driving it. Go back. Now, one thing you'll notice, it's a little bit bumpy, and that's something I'm going to have to debug a bit. But let's just drive around the track a little bit. And I've noticed if the bumping gets too big, then the physics simulation will actually fail, and Omniverse will crash right now. Isaac Sim will crash and it's because if those joints get way out of bounds, I think the solver just kills the solver. So yeah, we're just driving. This is the track we want to teach this thing to drive around. I want to get some more of this bumpiness out, and but everyone's on free days right now. Everyone but me doing this live stream. So everyone's out for the next few days, and Monday is Juneteenth. And so everyone's out for all the U.S. folks are out for that holiday. And I'm actually going to be on a family vacation next week. So I won't be doing the live stream next Thursday. But anyway, I think the Thursday after, I'm going to spend like that whole week just really digging into these physics issues and seeing if I can nail down. Yeah. Oh, there we go. Maybe we just crashed. It'll reset to the original position to stop the simulation. It's trying to recover. Boom. But in my experience, every time it crashes right now. So something's up with my masses or my joints. I have a whole bunch of articulations in this, which may be more than usual. Like each suspension setup each corner has 2 articulations. So I have 8 articulations plus like 2 or 3 in the steering. So it's kind of, a lot going on here. And let's give it a minute to die in peace. So what I'm going to show you today, first I'm going to show you how I've gotten this far, how I've got this rigged up, and then what? I'm going to show you how I wrote this extension. And then I thought we would just talk about the Jetson, right? I was going to show you kind of, I've got some stuff rolling in, right? I've been ordering parts and I've got stuff rolling in. So let's start with relaunching Isaac Sim. And I'll show you how I've rigged things. Yeah, and Zia is saying, I think we need some delta in damping in order to achieve a stable platform. Yeah, and I think also we need some compliance in the tires. Right now, the tires are just like, think of it as like a rubber bouncy ball, right? Whereas real tires have a lot of compliance. But at the same time, no, you might be right that maybe the whole thing is just too stiff, huh? And let's look at the units. Let's look at our stiffness. Let's see how it looks. Because part of the problem is the whole thing is just so light. I mean, the whole thing weighs a kilogram, and I think most robots in Isaac Sim are probably heavier than that. I did check I'll show you. We can go through some of the debugging I've done so far, and I really want to hear your thoughts. I can walk you through some of that. So maybe what we should do is see if we can debug that a little bit. Figure that out together. Yeah, and I've got some Zia saying that they've got some questions about the USD layers. Yeah, I'd love to hear your questions. And I'm still learning how to use those the most effectively myself. So we're going to want that maybe. I'll leave that open. All right. Let's just start by looking at the joints, though. There we go. All right. So you saw me rig this front left. I showed it to you, and then the rear left as well. And all I did was copied the front. I had the front and the rear. Actually, I had to redo the rear, but I just copied it to the rear and kind of, it's a little different because the front's got spherical joints on the outside. The rear has revolutes. And question, I can't give specifics. I don't know specifics, but the question is, are some updates coming regarding the performance of Isaac Sim? Updates are always coming. Kit 105 is coming out with a lot of improvements to everything. So yeah, we are flying over here. So yeah, updates are coming out. You bet. Okay. Question here. Was there any difficulty in terms of spherical versus revolute? No, you just have to know how you're defining it. And I think that the key there to making that, what I've learned over the last few, I've set up 2 or 3 of these now. The key is actually an on shape. And the key there is, I'll give you two tricks. One is having this template set up really helps, because I have a connector here for every joint. So I can go to the connector, I can double click on it, and I can look at its coordinates. And that works great for everything except for the wheels, because I've modeled each of my subcomponents based off of the global origin. And so the local coordinate system and the global coordinate system are the same. And so if it says, so here, if you look at a joint and it says, okay, what are the 2 parts? And then what's the position of the joint relative to the origin of that part? Well, you have to figure that out, unless you do what we've done with Onshape and you have everything relative to the global origin, which is actually a common skeletal modeling in practice within CAD anyway. So and the reason is because if you're working on a large assembly, so in aerospace, an assembly would have thousands of parts. Automotive too, right? And when you get to, so if you look in the CAD software, like if you look at Onshape, it has these really nice assembly constraints, which were great up to, I don't know, maybe 1,000 parts. But if you're constraining 30,000 parts together, forget about it. It doesn't work. It breaks. It's a mess. It's heavy. It takes forever to update. And so really what works better is just to have everything modeled from the global origin that you can, so that instead of giving it an assembly constraint, you just always have it at its at its 0 location. And what you do is you have it based off that origin, but then you build axis systems and datum geometry where it belongs within the overall assembly. So you can you model it in these local coordinate systems that you've built, but really its origin is at the global origin. And that's the way to go, I'd say, for large assemblies. It's just lighter weight that way. Anyway, so we're doing that practice here in Onshape. And so that means like and keeping in mind, oh, you know what? I wonder, I don't know. We should think about this. Well, but I measured it. Never mind. I was going to say the units in Isaac are meters. And if you look at these joint locations, that means that this one is at 13 meters to the back, right? That's interesting. Let's go to the Windows. If I go to extensions, there's a really cool extension. And it's the measure tool. Let's turn that one on. And so we can click this line and it can say, okay, how wide is this car? About 20 centimeters wide, according to this. I wonder if I make this meters. What? Oh, meters. Here we go. Let's try it again. Does it just tell us 20 meters? No, it's 0.2 meters wide. So that's interesting that I've got these modeled. Yeah, so sometimes I have trouble with the unit system. So just double checking that my spacing's right. And I do wonder if when we open something in Isaac, if it scales it or something. Yeah, I don't know. If we go to the physics, let's see here. Here's my physics scene. Gravity is 980. Distance time. Yeah, I built this in USD Composer. And I wonder if some of my units are goofy now. That's something I should try to figure out. And that'd be a good thing to really nail down so we can understand it. But I wonder if there's like a way to tell. Oh, Isaac examples. That's kind of cool. There's so many. I mean, Isaac is a pretty big app. Inspect physics. Oh, that's kind of cool. Oh, look, this is that extension we wrote. Interesting. USD unit converter. Oh, interesting. So that might be helpful. Physics utilities. Oh, wow. There's lots of stuff. All right. Nucleus check. Yeah, so some of that jitteriness. Some of that jitteriness might be coming from some kind of problematic units we've got going on here. So I think there's just going to be some debugging like that, fixing the units. You can add compliance contact to the two things. So I wonder if adding that to the tire material could help a little bit. I've played with that some. But basically just created those joints and it's looking pretty good. Let's take a look at the shock spring rate. Just curious. Yeah, I've got it at 10,000, which should be newtons per meter. From what I've read, 10,000 newtons per meter. So what does that mean? We're in like millimeters here, right? Really? And so we want to go like 1 millimeter should be like 1 Newton. So like when we set this car down, but with 1 kilogram, I think I want those shocks to go about a millimeter. Because if I with my real car, when I set it down, first of all, there's no preload at all. So the joint starts there. And then when I set it down, oh, you know what? It's going more than I thought. Maybe more like 2 millimeters. So maybe it wouldn't hurt to soften those springs a little bit. Should we see if that helps? I can select all of my springs at once here. And I can add them together so they kind of stay together. So right now it's at 10,000, which means that that's pretty stiff. 1,000 should be that under 1 kilogram, it should flex a millimeter. Let's see how that looks. Yeah, that's not stiff enough. I mean, I don't know if we could even drive. Let's see. I don't think I'm connected yet. Yeah, it's stuck on the ground. But maybe let's try for less than 10,000. Let's just kind of just bump it up a bit at a time until it sits off the ground, you know? Still on the ground. Let's go all the way to 5. Oh, there we go. See there, it like it sunk down a bit and came back. Let's try that, see if it's any better. Oh, look at that. That's way better. So the wheels are still bouncing, but the chassis is not bouncing nearly as much. Okay, that's a little bit better spring rate. And for the bounciness, I actually wonder if we could. One thing I noticed is that these are all meshed with SDF meshes. So if I go to Tools or Window Simulation Debug, and if I go to the Enable Debug Visualization, oh, what's this do? Whoa, that's kind of cool. Kind of a cool visualization. No, I want the this one though, because it lets you do lots of stuff. We want the collision shapes. Then when we run, you're going to see all of our colliders. And let's just get a look at the. Oh dear. Let's look at this collider here. And I wonder if, because it's a mesh and it's not exactly smooth, I wonder if that's part of the problem. Because it's like the tires start to spin. And then they bounce, you know? So let's take a look at these tires. And what I can do is I can filter by colliders. Then I can only select colliders. And let's find those wheels. And I've goofed through this a little bit. I happen to know that mesh 1 is the tire, mesh 0 is the wheel. So let's select those tires, all 4 of them. And we can go down to look at the tessellation and look at some options. So we've got the SDF mesh. And okay, triangle mesh. The SDF meshes are supposed to be really good. I mean, it's a good looking mesh, that's for sure. I tried a bounding sphere, but the wheels wouldn't turn because it didn't. They would just slide and roll no matter what. So I think SDF mesh is still what we want. Let's bump this to like 750. See what it looks like. Give it a minute to update that mesh. A spherical convex hole approximation. Do you know what we should do? Is there's a sample of this dune buggy you can drive around. We should see how they rigged up their tires. It doesn't look that much different. Let's see how it drives better. Let me get behind it. I'm actually in my chase cam. Well, you say that hopefully it will have cylindrical holes. Ooh, that's not really better. Look at that. What do I have selected? Look at those tires. Oh, those are the, I know why. It's because they're all going at different rates and I have them all four selected. That's nothing to be worried about. Yeah, didn't make a difference. Actually might have made it worse. Yeah, let's go ahead and stop that. Here, let's see here. But let's save this scene. We've made some progress with that. That spring rate's looking better, I think. All right. So now check this out. This is how I figured out how to do the controller, by the way. I go to Window, or is this it? Yeah, Simulation, Demo Scenes. And there's this really cool demo under Complex Showcases. There's a Lego Technic buggy. What did I do? Oh, I opened it twice. Yeah, so this thing, if I filter by joints, and if you look at that engine's going in there. The steering wheel goes. Uh-oh. So when I steer, the steering wheel moves. It's like a whole bunch of joints in there. And let's change to one of these cameras. The drone camera is pretty good. And it's really looking pretty good. You know, it's not bouncing and jittering like. Let's do the follow camera. Oh, actually, the cockpit camera is maybe more rigid. Yeah, so this thing is behaving really well. I'd be delighted if ours worked this well. So we can take a look at this a little bit, look at some masses and see where we're at, look at some spring rates, see if we can find a trick. But those tires are even pretty, and they're bumpy on purpose, you know? Let's see. Let's take a look at, is there like a shock? Here you go, spring 14. That's a prismatic, yeah. Look at that. Stiffness is 200. Damping is 10. So that's in the same range as us, you know. Let's pick this collider. Let's see what we get here. How is it modeled? Convex decomposition, which is not even as good as SDF. So that's not our problem. You know what? And any thought? Damping is low. Let's take a look. Let's look at that spring 14. Oh, look how low the limits are. The limits are pretty much in the same spot. Like both at 0. I wonder if that makes a difference. So it just basically said there is a limit, right? And then the damping is 10 to the stiffness is 200. Let's fiddle with that with our scene. See if that helps. So it's maybe 5%. Would you like to save the stage? Don't save. We could try that. Maybe let's tweak the damping first and then go do the convex decomposition after that. Let's see. Joints. Let's grab those three. U. Oh, there's 4. There we go. And let's go to those limits first. There we go. I just put a tiny limit on it. Let's see if it changes at all. Oh, we're not connected. No difference. Okay. About the same there. And then see if we want to bump it up to like 250 if we want to go the same percentage of damping. Ours must be a lot heavier. Yeah, maybe a little better. Although I noticed that the car sags quite a bit. It's almost to the ground now. So I think I would bump that back up to 10,000 and make this 500. See how that looks? No, not better. I think we were pretty good where we were. Yeah, so I'm going to have to figure this out. I think somebody internally might have some good tips for me, you know? Yeah, let's try the convex decomposition. Let's see if that works better on those wheels, you know? Why not, right? You. And right now your SDF mesh convex decomposition. Wow, look how much. That's a lot. Oh, that's worse. And the SDF mesh looks really a lot better, I thought. I'm going to go back to the SDF mesh. Oh, I wonder if they have any of these advanced settings. Oh. Let's I don't want to save any changes we made. Let's go back to that demo scene and see if they have those. We can also look at their material. Let's see. Load scene. Don't need to save this. Just curious what material this is. Wow. It's just whatever the default material is. Interesting. Let's look at the physics scene and see if there's a default. What? Just a default material? Really? So they haven't done anything special with the materials here. Well, there's got to be some material. Like if I click on this, let's remove this filter. Yeah, so here's your wheel. Where do they apply the plastic material, though? Okay, this is kind of weird. Yeah, I don't know. Because here's the material, and it's basically saying there's no material applied. But there's certainly material applied because it's, looks like black plastic. Materials. Oh, there really are no materials in this. I'm not sure how they did that. Okay, but it's certainly not there. Let's take a look at the joints. Let's look at that spring. Oh no, we were going to look at the collider, weren't we? There we go. Let's remove some of these. Go to colliders. There we go. And advanced. Oh, look at that. They have a little bit of a contact offset and a rest offset. 0.02 and 0. I wonder if that just helps it out a little bit, Error percentages, those are all default. So let's take a look at that contact offset and that rest offset to see if that would help us out. Min thickness. Let's take a look at our colliders. Grab our 4 tires. Go to our advanced. Oh. Let's see what happens here. Probably have to connect it again. That's not really any better. Oh, and I just crashed it. Shoot. Yep, it just choked. So I think I'll ditch those. Yeah, I'm going to have to reach out to some people who know more about this than I do and see if I can get some help, because it maybe has to do with the masses, I guess. But let's take a look at how I wired up that controller. I'll show you how I did that next. And yeah. And by the way, just so you all know, this is usually so far it's always been my fault that when things are kind of glitchy like that, there are ways to get around these things if you understand how the solvers work and stuff, which I am learning, to put it in perspective. The first time, I mean, you see that one. I should show you the last car I did, just to give you some perspective. I'll show that to you. Okay, this is a remote control car I did before, and I was designing it completely from scratch. But look how bouncy and weird it drives. And you see that plate is still like bouncing and floating. So, yeah. And you can't steer it with a controller. It just kind of goes forward and turns to the right. And you look at that, look at the steering kind of like wobble, and So now you compare that to this current one, and you'll see, and it's not, this is not that Omniverse has changed. This is that I have learned how to rig things a lot better. And so, yes, I know it's bumpy, but honestly, if we switch to like the perspective camera, you probably won't notice nearly as much, because you really notice with that camera because it's attached to the chassis. So if the chassis bumps at all, you really notice. Yeah. So, I mean, as far as like, it really looks pretty smooth from here, you know? We're making progress. And that, remember that first video I posted, you could totally tell it was like jittering and wobbling. So we're making some progress. Yeah. So like something breaks and steer the other way. Yeah, that's right. So basically when it crashes like that, what's happening is one of the joints is getting so far out of whack or reversed or something so that it cannot, because with those joints, like with a spherical joint, it's saying that those two points on those two parts should be stuck together. So if the solver gets in a state where it cannot bring the positions together, if we were using the video game solver, it would be like, oh well, they're just apart a little bit, and it would try to bring them together. With this articulation solver, it just breaks it when that happens, and that's a good thing, because that means that we want the stricter solver that doesn't let us get away with that fuzziness, so that we can eventually get accurate forces and physics out of it. But our physics have got to be dialed in, or else it'll break. All right. Yeah, honestly, I should be less whiny about this. When I'm just on this camera, that's looking pretty dang good. I should be happy with where I'm at, you know? Oh yeah, it's looking pretty smooth, isn't it? Yeah, let's get into that controller, okay? And this is how I did it. First, I knew that Lego Technic buggy existed, and I knew I had the code, and that is a big tip. So if you go to Windows Simulation and then Demo Scenes, there are all these demos. And a cool thing about them is they're all built from scratch with code, or they're all built with code. And so you can go to this Lego Technic buggy, and then we can say open source. And this is the code that builds that scene. It does bring in that prearranged buggy asset with the environment, but this is setting up the it's listening to the controller, it's setting up the steering, and this was really a huge head start to getting this set up. And I just noticed here in Isaac, where was that? Isaac examples. So cool. Look at how many Isaac demos we've got. That is cool. Should we check one of these out real quick? Whoa. That is so cool. Press the Open in IDE button to view the source code. Open source code. It's opening. Wow. Oh, cool. This is a whole bunch of code. Oh, wow. Look at these. Oh, these are all the examples are in this one folder together. That's nice. So, yeah, if you want to dig into Isaac a little bit, then those are some great samples, and I'm sure I'll be doing plenty of that. So let's look at this extension that I wrote. Windows, if I go to extensions, and then if I go to third party, here it is, and I can open the source code in VS Code. And Oh, we want this one. All right. So this JetRacer, I just copied and pasted that demo code, and then turned it from a demo class. So from a class that inherits from demo to just a bare bones class, and then stripped out everything I didn't need, like their sounds and stuff that I don't need. So for the extension, I just made it so it's a single button, and here's the connect button, and it subscribes to the physics step event. Oh, calls in the buggy class that I copied. It calls its create method, and then it registers for the physics step. And the physics step, all it does is calls the car to update, because like pretty much all the code I needed, all the events and stuff were already in this JetRacer, or this. Well, it was called like Lego Technic Buggy, and I changed it to JetRacer. The one big difference is that its steering was a rack and pinion with a prismatic joint, and so I've actually got the servo modeled in mind. So I had to change that to a revolute joint and tweak the steering settings to steer where I wanted to, in particular the steering gain. But basically what we're doing here, we're setting these constants. Like when you go forward, you have to set you put these drives on the joints you want to drive, and you have to set the stiffness and the damping of those joints, as well as the max velocity here. And then I added steering settings to do the same thing. And these are copied. We're driving the steering like similarly to the drives, except it's by angle instead of by velocity, but similar properties for those. Yeah, let's see here. JetRacer. So here's where we create it. We just grab the stage, set everything to 0, like where we're steering and stuff. And then we grab the prims that have those joint drives on them. And to prep before you do this, I had to come into the scene. Let's look at our joints. If you look at the rear, front left, let's just look at the, here we go, wheel rear right. That's one. If you look, I had to, here's the drive properties. And to get those, you go add, physics, and then there's going to be a joint drive option if you haven't added it before. And so then you can say, you can set the damping and stuff here, but we're going to let our code do that. So you don't have to set any properties here. The code does that. You just have to make sure that the drive is there so that the code can access it. So we're going to grab each of those joints, right? We grab the chassis, and the chassis, so that we can tell how fast it's going. I wonder, that's interesting. Max drive velocity. Oh, this is how fast the car can go. Let's just double check as you go that that's not how fast the wheels can go. But yeah, we're going to grab the joint because we'll track how fast it's going to set the max velocity. We're grabbing the 4 wheels because it's a 4-wheel drive vehicle, and we're grabbing the servo arm. Those all but the chassis. These 5 already have a joint with a drive on them. The chassis is just a rigid body, what we use to calculate velocity. And this was all in that Lego demo. So I didn't come up with this myself. I just copied somebody else's work shamelessly. Where are we at? Here we go. App window.get gamepad. This is a handy one. And then here's carb.input. And so we're going to subscribe to the gamepad and call this on gamepad function. When we shut down, we're just going to unsubscribe and set stuff to null. By the way, I call shutdown from the extensions shutdown function. At least I should. Do I? I do. Yeah. Good. I was going to be embarrassed if I wasn't doing that. Okay, so for update, we grab the velocity of the car so that we can set the speed. We'll take a look at this later, this self.speed. Then we're going to update the steer angle and update the drive. So update steering angle just calculates, are we trying to steer right or left? And sets, now this gain is going to, wasn't on there, it was going to be wrong because it's for that prismatic joint. You just tweak it until it's steering as much as you want. Hey, welcome, Brotsit. Welcome to the party. And then, let's see. Yeah. Now for an angular drive, so if we want to set a servo to a specific angle or set a joint to a specific angle, then you want low damping and high stiffness. And that's just going to basically say, that just sets it so that it's like a rigid connection, if you will. And whereas you want the reverse, you want a low damping and a high stiffness if it's a velocity drive. All right. Update drive does the same thing. It's got a little more logic because it's can go forward and reverse, but essentially you're doing the same thing. Is if the throttle's on, you're going to set it to go forward. But let's take a look for that self.speed and see where that comes into play. There's speed there, right there. If throttle is less than 0.05 and self.speed is less than 10, then keep going. I kind of have a theory now. Let's bump this up to 20. See what happens. I kind of wonder if our joint speed is crazy high, and so it's just making those wheels spin, and our car speed is low. Yeah. Oh, and because of our units, maybe that's what's going on. Let's try that now. Let's connect the controller. Oh, that'd be so cool if that was it. Oh, hello. I don't know about that. Yeah, what is the... Oh, yeah, we're doing it right now. Look, we got this kind of fun, what a title, looking forward to it. Yeah, we're right here. Look, this is a physics simulation of a remote control car, and I'm driving it right now with my gamepad inside of Omniverse, all set up with USD joints. Yeah, yeah, it looks great already. We're getting there. It's definitely getting better with these incremental improvements, right? Getting our masses right, getting our spring rates right. Just little thises and that's at this point. I wonder. I'm going to debug this real quick. I wonder if our speeds. Sometimes I get this thing where it kind of gets cached. Oh dear. Okay, this is what we're going to do. I'm going to go here. I'm going to crank it up the speed here. And let's see what the speed is. Oh, wow. Speed's 70 right now. Okay. Is there another speed? That's interesting. I didn't see that coming. Because it's supposed to say not let the speed get over 20. Oh, if the throttle is less than... Oh, that's if it's going slow. Okay, so it's going slow. It's like... what's it doing? Oh, I see. So basically, if nothing's happening and this slowing down, is going to go ahead and stop it, so it just doesn't roll forever. Oh, I see. If throttle is greater than brake. Yeah, so it's just going based off the maximum joint speed. And I have noticed if I crank up this joint speed, then the wheels start to spin and bounce, and then my simulation gets out of control. So we'll just go back to where that was. So that wasn't it. And for those of you who are just joining us, if we change to our chase camera, and now you'll be able to see that there's still, let me connect here. What did I do wrong? There you go. Yeah, you can see that it's bouncing a bit. So it's a little bit bouncy. And we're trying to work that out all the way, you know? But also so I'm just kind of keeping my eye out for things that might be causing that. And one of those I thought might be that. I thought that was a max speed, but really it was a minimum speed. And we can crank this drive velocity up, but like I said, it starts to make those wheels spin instead of get traction, and then they get really bouncy and things get wild. Which, to be fair, happens with a real remote control car. You know, if you lay on the throttle, the wheels start to spin and bounce. It's just we're not trying to keep track of all those positions, and I don't know. That doesn't crash our simulation in real life. Let's see here. Brake. Yeah, so there's our throttle code, and then here's the gamepad input code. All it's doing is it's detecting that trigger and the left stick to see where we're at. So, and yeah, there we're at. And like I said, once again, you can get all this code. I just paired it to just cut stuff out from that Lego Technic sample that comes with it's that sample that comes with any of your Omniverse apps, one of those physics samples. All right. Well, we've only got 5 minutes left, and I just wanted to do some show and tell. Okay. So for those of you who are new here, or those of you who aren't, I've got, so that car, and we're going to have to work on the dimensions at some point here and really dial them in. But that is, it's got all the same geometric control points as this one. Now we've got to measure, we've got to move them around, we've got to just make it match. But yes, I love this response. Oh, it's real. Yeah, it's real. Okay, here's the real one. Okay, and I'm going to go ahead and post the link to this build. This is just a kit. Like, I've got my controller right here, and I can just drive this thing around, right? In fact, my son loves it. He's 2. He just can't get enough of this car. And let me pull up this repository and share it. Here it is. All right. So this GitHub project, yeah. Well, the original JetRacer has a base RC builder kit. That's exactly what I did. Is I went to my hobby shop and I bought this remote control car and I built it. It was fun. And then you can start to, it also has STLs. I 3D printed this one on my 3D printer. I had some quality issues. It sagged, it's warped because I have a resin printer that has great resolution, but not the best strength. It's also pretty, I just broke it. Yeah, not the best part. We're just gonna throw that away. And so he actually has a link to this Donkey Car site where you can buy all those 3D printed. And I ended up doing that because my 3D printer can't even print the full size. So for that one, I had to chop it down, and I was able to do that without cutting off any of the mounting points. But then the actual mounting plate is just as big and has critical mounting points all the way to the edges. So I had to order it anyway, or buy a PLA printer, I guess. And I decided it would be cheaper to just buy the parts for now. Yeah, so I've ordered those parts. I've got myself a Jetson Orin Nano, which is going to be the brains of this guy. And for this project, you could just use I think any of the Nanos. The reason I bought the Orin is because, in my opinion, or my hopes, this is only our first project, and I hope we do even bigger and cooler projects. And so I bought a little bit more high-powered Jetson, just so that Oh, that's interesting. Sorry. So I ordered the bit more higher powered one to support these future projects, and I'm not going to order a new Jetson for every project. I've just got the one. But yeah, and this is kind of cool. PCB way, you can order, so you give a 3D print file and they 3D print it or even machine it. That's cool. Great question. Do you need them for all the sensors? Okay, so when I was talking to Chitoku Yato, he's from the Jetson team, and we had him on a few weeks ago. And man, I asked him, could we put a LiDAR on the Jetson Nano, on the original? And he was like, yeah, but he wasn't. I could tell he was like, it seemed like you can, but that's pushing the limits of that particular piece of hardware. Whereas with the Orin Nano, it's like, yeah, we could do a LiDAR next if we want, which I think would be great. I think that would be great to do a LiDAR or other sensors. Great question. Let's see here. And yeah, I think they both support to Zia. What he's saying is the Orin supports LiDAR. I think they both support LiDAR. I think really what it boils down to is how big of a model can you deploy. And I think that if you're using LiDAR, you're probably going to want to have, you're going to have a bigger model to be able to handle all that data. And so I think you could just use a LiDAR sensor and just still have the same size model that your Nano can support. But with the Orin Nano, you can do like 8 times as big of a model. And so I think you're going to be able to have a model with more variables that can support more sensors and just more stuff. So there you go. I mean, but they all have, USB. They all have connections. I'm pretty sure you could do yourself a LiDAR sensor on this if you want. And let's see here. Oh, other stuff I got. Just stuff's been rolling in. I've got my Wi-Fi antennas here, and then some hardware right here, and then I've got my first. Here's my wireless card, so my Wi-Fi card with Bluetooth. So that's nice. So in theory, we should be able to. I mean, you could save yourself some cash. In theory, I haven't gotten this to work, but with this and the Nano, you ought to be able to just use a Bluetooth gamepad controller and connect that to your Nano and control it with that, right? How long to build the kit car? I don't remember. It was just kind of fun. I lost track of time. I don't know. If you just sat down, I think you could build it in a day, especially if you were experienced. I was my first time, so I made some mistakes. I mean, some embarrassing. I even made it up. I was looking at the instructions, and they had this tube, and they were showing that they were putting some liquid onto some of the parts. And I was like, oh, it must be model glue. So I was looking for model glue, and luckily I asked on an RC forum, what's the best model glue for this? And I looked again. It was actually asking you to put lubricant on the parts. So it's really a good thing I didn't glue those parts together. And for your reference, the RC experts all said they just don't do the lubricant because it just attracts dirt and makes things worse in the long run. It just makes it all messy. Yeah, Zia says extra stiffness, and yes, that would be unfortunately it'd be extra stiffness in all the stuff that's not supposed to be stiff, all the stuff that's supposed to move. So there you go. I've got more parts rolling in. I've got the base plate rolling in, and I've got just all my stuff. And so hopefully a week or two from now, you're going to see this real car, but it's going to have a Jetson Nano on there. And I'm thinking we've got probably good enough physics. I think the next step is going to be to basically have this thing drive forward a meter and go back a meter, something simple like that. And and then get the to do the same. And great questions. You measured all the parts during assembly. I weighed them, so I have their weights, and I measured the dimensions of quite a few of them, the ones I thought would be hard to get access to. I have ordered a camera. Yes, yeah, with a wide angle, 160 degree, kind of almost like a fisheye lens camera. So, yeah, we're just on our way. So, I think that's so next. I think we're going to, and I think a really important thing is to come up with a pipeline. And from what I've read, a lot of people deploy to their nanos using a container, which I frankly don't understand very well yet. We're going to dig into that. We're going to figure out how to, because, so what will be really nice is if conceptually a container is like a VM running on your computer, but just very, very bare bones. And so if we could have a container running on our local computer and Omniverse is getting its instructions from that container, and then we ought to be able to just deploy that container directly to our Jetson, and it should work the same, behave the same. And it's, in a way, it should be like an emulator, except it's not an emulator. We're not emulating the Nano on our computer. We are creating a container that works the same on our computer and on the Nano. That's my current understanding of how we'll do this. So, but yeah, we're assembling the real car. We'll go ahead and build a container, I think, and see if we can get that going. And yeah, I think Zia is saying that Papa Chuck, yeah, he's the VM container ecosystem guy. So we'll definitely, hopefully, get some of his help. So, all right, it's been another wonderful EDIO. Thanks for coming, and I'll be out next week, but we'll see you the week after. Have a good one, everybody.